Hello, in this second part of Laplace transform series, we will see some worked out examples using the basic definition of Laplace transform. So this is the definition of Laplace transform which was seen earlier. Using this, let us find out the Laplace transform of t. So what will be the Laplace transform of t? We already seen given you the table of transform in the last lecture. This is going to be L of t is going to be 1 by s square. So let's see how we arrive at it using this formula. So L of t, if we use this formula, it is t into e power minus st dt. So this is the product of two functions u and v, first function, second function. So integral of product of two functions uv dx is u into, that is u is the first function into integral of the second minus integral of derivative of the first into integral of the second. So this is a formula. So using this, we will take t as u, first function, e power minus st is the second function v. So first function t into integral of the second, e power minus st by s minus s. Integral of e power minus st is integral of e power minus st by s, e power minus st integral is e power minus st by minus s, minus derivative of the first, derivative of t is 1, and integral of second is e power minus st by s. So this is t into e power minus st by s, and integral of e power minus st is minus 1 by s. So minus of minus becomes plus. This another s is here. So this minus of minus is plus, and integral of e power minus st is minus 1 by s. So there is already s, so 1 by s square. So into e power minus st between the limit 0 to infinity. So this is minus and minus plus. This minus is because integration of e power minus st is minus 1 by s. Minus 1 by s into s is 1 by s square, minus 1 by s square. So this first term becomes 0 in both the limits. When you put t equal to infinity, e power minus infinity is 0. When you put t equal to 0, this is because t is 0, so the whole thing is 0. So the first term becomes 0 in both the limits. The second term is 1 by s square. Again, e power minus st, when you put t equal to infinity, is 0. And the lower limit, when you put t equal to 0, it is 1, so minus 1. So minus 1 by s square of into minus 1 equal to plus 1 by s square. So L of ft, that is L of t, where f of t is t, L of t is 1 by s square. The next example is, we will find L of Laplace transform of sine kt using the basic definition. So L of sine kt, if you apply the formula, is integral of e power minus st into sine kt dt. It's from 0 to infinity. So I just call this as I. Okay, I just call this as I. This is nothing but L of sine kt. I'll call it as I. Now if you apply this is again product of two terms u into v. If you apply the rule, first function, let us take u as e power this, let us take this as u and this as v. So u into integral second function, integral of v, integral of sine kt is minus cos kt by k, minus integral of derivative of the first. Derivative of the first is derivative of the first, e power minus st, derivative is minus s into e power minus st, and integral of the second is minus cos kt dt. This is dt here. This is dt. dt. Okay, so 1 by k is a minus sign here, minus 1 by k e power minus st cos kt, and minus minus minus, 3 minuses, so minus s by k into integral cos kt into e power minus st dt. So once again, product of two functions, integral of product of two let's take this as u and this is v. So this first term I written as such, second term minus s by k, first term u e power minus st, integral of the second, integral of cos kt is sin kt by k, minus integral of derivative of the first, derivative of the first is minus s into e power minus st, and integral of the second sin kt by k into dt. So this term is written as such, and again minus, I'll take s, k is common here, one more k is common, so I'll take minus s by k square common, minus s by k square into e power minus st to sin kt between the limit 0 to infinity, and this term is minus minus minus, so 3 minuses, so minus s square, s into s square by k into k square, minus s square by k square into integral of e power minus st into sin kt, this term. Now if you see, this is nothing but our I, this term is nothing but I is nothing but integral e power minus st sin kt, so this is nothing but I, this term is nothing but I, so I'll call this, replace this by I, remaining all I written. On the left hand side is L sin kt, left hand side is L sin kt, which is nothing but I, so I equal to this term as such, minus s by k square e power minus st sin kt, this term as such, and minus s square by k square into I. So if you take I to the other side, left hand side, I into, this is 1 plus s square plus k square, equal to, remaining terms are written as such, this is the first term, and this is this term, and this one is I into k square plus s square by k square equal to, here I take an e power minus st common, e power minus st is common, okay, e power minus st is common here, so I take an e power minus st common, and also I take an k square common, so this term becomes k into cos kt, this becomes k into k cos kt, and this becomes s into sin kt after taking s by k square common. And if you substitute the limits 0 to infinity, this term in the upper limit infinity, when you put substitute upper limit, the entire term becomes 0, okay, because e power minus infinity is 0, and cos kt and sin kt are finite values even at infinity, so the upper, when t equal to infinity, whole term becomes 0 because of this, so only the second lower limit term exists. When you substitute t equal to 0, this becomes 1, okay, this becomes 1, second term minus of, second term has a minus, and this minus already, so minus of minus becomes plus, second term, second limit, when you substitute the lower limit, there will be minus sign, and that minus and this minus makes it plus, so 1 by k square, when you put t equal to 0, cos 0 is 1, so k cos kt is k, and sin 0 is 0, so it is 1 plus equal to 1 by k square into k, that is simply 1 by k. So I into this, I into k square plus square by k square equal to 1 by k, or I equal to k by k square plus s square. That means I is nothing but what we had defined earlier as I as L of sin kt, okay, I is nothing but L of sin kt, so L of sin kt is k by s square plus k square. Now we will do this by an alternate method, which will be much simpler, a lighter alternate method for the same work. Here we will also illustrate the Laplace transform of derivatives, okay. In this method we also illustrate Laplace transform of derivatives. So f of t, let's take f of t is our f sin kt, right, f of t sin kt, first derivative is f dash t is k cos kt, second derivative is minus k square sin kt. So if you rearrange this sin kt equal to f double dash t by minus k square, that is 1 by minus 1 by k square into second derivative sin kt. So if you take L on both sides, L of this side, L of this side equal to L of this side, L sin kt equal to minus 1 by k square into L of f double dash t. Now what is the Laplace transform of derivative? We have seen earlier, nth derivative Laplace transform is this whole thing, right? Laplace transform of nth derivative is this. By using this, you will use this formula for the second derivative. Laplace transform of second derivative will have 3 terms. So Laplace transform of second derivative is s square by using the formula in the table of transform. Laplace transform of second derivative is s square into L of ft minus s into f0 minus f dash 0. Whereas f0 means f of t evaluated at t equal to 0, f of t is sin kt evaluated at t equal to 0, sin 0 is 0. F prime 0 is first derivative. First derivative is k cos kt. Ft sin kt means first derivative is k cos kt. In this evaluated at t equal to 0, cos 0 is 1, so it is k. So if you substitute this, in the above equation, this equation, L of sin kt equal to, this is nothing but L of ft equal to minus 1 by k square into s square L of t f of t minus 0, this is 0, this is k. So if you simplify this, we get this L of ft into 1 plus s square plus by k square equal to 1 by k. If you simplify further, L of ft equal to k by k square plus s square, that is L of sin kt equal to k by k square plus s square, which is the same as what we got by the previous method. So this method, second one, is a simpler method. It also illustrates the Laplace transform of derivative. Laplace transform of second derivative here. Laplace transform of second derivative is applied here. So it also illustrates the use of Laplace transform of derivative. So we'll have more examples of Laplace transform in the next lectures. There is a correction because I have made a small mistake in the sign in the last step of the previous method. So let me go back to the previous method in the last step, and so let me correct the mistake. Here, mistake is here. This is the last step of the previous method where we found the Laplace transform of sin kt. So this sign must be plus, because minus, I have taken minus common out, so this must be plus. This must be plus. This term must be plus, okay. This must be plus, and similarly this also must be plus. Both must be plus. So let me correct them. Let me correct the sign. So this term is made plus. This term is plus now. It should be plus. Plus is the right answer, right sign, and here also plus. So when you substitute the limits, as I had explained previously, you get this. Anyway, there is no change in the final answer. Final answer still remains the same. Final answer still remains the same. Final answer still remains the same, k by k square plus s square, because of this 0. So only mistake was this term should have been plus. Earlier I shown it as minus. So this should be plus. Please read it as plus. And the final answer is same as before. I is k by k square plus s square. And it's a small mistake. Makes no difference in the answer, but still the method should be right. So this sign is plus. Okay. So we'll come with more worked examples of Laplace transform very soon in the next lectures.